Now that we've learnt rules for combining functions and rules for differentiating new functions, we've got a lot more in our toolkit. We're going to go back and revisit what you saw in year 1 differentiation on increasing functions, decreasing functions, and convex and concave functions. We'll start with the first derivative and make sure we understand how that works, because the second derivative behaves in relation to the first derivative just the same as the first derivative behaves in relation to the original function y. So let's start with the first derivative. dy by dx tells us the rate at which y changes as x changes. So for each small change in x, what is the corresponding change in y? And a good way to think of this is as the gradient. So when you see dy by dx equals 7, it means that y is increasing at a rate of 7 units of height increase for every 1 unit that x is moving along. That means the sign of the first derivative tells you whether or not y is increasing. If the first derivative is positive, it means we have a positive gradient, and therefore the curve is going up. As you move along in the positive x direction, or as you move to increase the value of x, the effect is, at that particular moment on the graph, to also increase the value of y. And vice versa. If dy by dx is negative, that means that for a small change in x, you're going to see a negative change in y, so the curve is going down. We've got a graph here. It might look familiar to you if you've been doing stats recently. This one is y equals e to the power of minus x squared, a function which previously you didn't know how to differentiate, and now, incidentally, you do. A little bit of chain rule. We're going to use the fact that the first derivative sign tells us what this function is doing, and you're going to annotate a graph that looks like this one. So if you can do a quick sketch of the graph, then what I'd like you to do is indicate on the graph anywhere on the graph where the function is increasing. If the function is increasing, mark it as increasing on the graph. You can do this by color coding it if you like. If you've got lots of different colors, feel free. The regions where the function is decreasing, so if y is decreasing, you need to indicate that on the graph. That will correspond to a negative dy by dx, negative gradient. And finally, the points where it changes between increasing and decreasing, or in some cases, depending on the graph, it might be increasing and then stationary and then increasing again. That happens with y equals x cubed, as we'll see shortly. But any points where the gradient itself is 0, we call stationary points. It's not going up, it's not going down. At that moment, it's doing neither, so we have a stationary point. When you throw something into the air, for half of the motion, it's on its way up. For the other half of the motion, it's on its way down. And at the single moment in between those two phases of motion, which is not a period of time, it's just an instant in time, it's a single moment. At that single moment, you could argue that the object is neither going up nor going down. It's at its highest, so it's not on its way up, and it's not on its way down yet because previously it was no higher. So it's not coming down from anywhere, it's not going up to anywhere, it's neither going up nor coming down, it is stationary. Here's what the graph should look like if you've managed those. Throughout the negative values of x, the curve is always increasing. Sometimes it's increasing more quickly, and sometimes it's increasing more gradually, depending on the steepness of the slope, but the function is increasing for all negative values of x. The function is decreasing for all positive values of x. And in between, when x equals 0, we end up with a stationary value. In this particular case, that happens to be a maximum. And in order to identify the nature of that, you might use a second derivative test, which we'll talk about in a moment as well. But as we're going to see, the second derivative test may not be all it's cracked up to be. But let's first see if we can be a bit more rigorous with this. You've drawn on the graph where it looks like the curve is an increasing curve and where it looks like it's decreasing, and obviously where it appears to change. But can we use differentiation to verify those results? Well, yes, we can. We've got chain rule for this. If y equals e to the power of minus x squared, we can differentiate e to the minus x squared because we can differentiate e to the power of anything, as long as we can also differentiate the anything. e to the something differentiates to the same e to the something multiplied by the derivative of the something. The derivative of minus x squared is minus 2x. So we just bring a minus 2x as a factor of our term. E to the minus x squared becomes e to the minus x squared multiplied by the adjustment factor minus 2x. And if we're interested in where the function's increasing, where it's decreasing, and where it's stationary, well, all of those facts hinge on where does it have a gradient of 0. For looking at stationary points, gradient of 0 is exactly what we want. And if we want to know where the function's increasing, we want to know the entire range over which it is increasing. The point when it stops increasing is the bit we're interested in. To describe the range, we care about that point. You can see where I've written down at the bottom here, y is increasing when x is less than 0, y is decreasing when x is more than 0, and y is stationary when x equals 0. In every single case, we referenced the value of 0 because that's what we care about. Either that's the point we're talking about, or that's the boundary point for the region we're talking about. So let's see what happens. We find stationary points first. We set that equal to 0, and the only way we can get negative 2x e to the minus x squared to equal 0 is if x equals 0. You can think of that as being the product of two functions, minus 2x and e to the minus x squared. And e to the minus x squared is never going to be 0 because it's e to the power of something. Think about the graph, y equals e to the x. It approaches but never quite reaches 0 as x approaches negative infinity as you move to the left. A lot like the green section of this graph, to be honest. But as x increases, then e to the x also increases. It never gets to 0, and it certainly never goes below 0. We can also find where this curve is increasing by thinking carefully about what happens for different values of x. We've already said that e to the power of anything is always positive, so all we need to worry about is what happens to the rest, the minus 2 times x. Well, when is that going to be positive? It's going to be positive when minus 2x is positive. And minus 2x is going to be positive when 2x is negative. And 2x is negative exactly when x is negative. So we just need negative values of x. That will give me the solution to minus 2x e to the minus x squared must be greater than 0. And the same thing, but the other way around, gives us the values for which the curve is decreasing. Now let's look at the second derivative. The second derivative, d2y by dx squared, or y double dash if you're using that notation, that tells us how the first derivative changes. Just like dy by dx tells us how y changes with respect to x, the second derivative, d2y by dx squared, tells us how the gradient dy by dx changes, which makes it a little more subtle. We're talking now about the rate at which the gradient changes instead of just the rate at which the function changes. And on this graph, you need to look quite carefully to identify which bits of the graph have a positive second derivative and which bits have a negative second derivative. It's not about whether you're going up or going down. It's about how the gradient of the slope is changing. When I went out cycling with my kids today, we cycled up a steep hill. There is a difference between cycling up a steep hill which is getting steeper and cycling up a steep hill which is gradually leveling out. Both of them have a positive gradient. It's an uphill slope. But in the case of the second one, where the slope is getting less and less steep, the work is becoming easier. It's still hard work. You're still pedaling uphill, but it's becoming less and less difficult as you go up. That's the difference between the first derivative and the second derivative. We call a curve with an increasing gradient convex. And the best way to think of this is to have some concrete examples in your head. I like to remember e to the x because it's the last two letters of the word convex. A convex graph is a graph which is curving in that upwards direction. You've got to be a little careful with this though. It doesn't mean it's going up necessarily. E to the x is the classic one to remember because it's got an e and an x in the spelling of it. But it's not the only graph that is convex. Another nice straightforward graph you can keep in your head is y equals x squared. This is convex everywhere as well. These are two graphs that are always convex for all values of x. That means the gradient is always increasing. Another way to say it would be the second derivative is always positive, no matter where you are. In fact, for y equals e to the x, both the first and second derivatives are e to the x. So of course they're both positive. For y equals x squared, the first derivative is 2x, which is sometimes positive, sometimes negative. That's why the graph y equals x squared is sometimes decreasing and sometimes increasing. But the second derivative is the derivative of 2x, which is 2, which is, of course, always positive. That's why, even though the graph of y equals x squared is sometimes decreasing and sometimes increasing, the gradient of y equals x squared is always increasing. Either it's a steep negative becoming a less steep negative, or it's a positive becoming a more steep positive. And you get the exact opposite effect if you try a y equals minus x squared graph. If you throw something in the air, then the position will change. It'll get higher and then it'll get lower. The velocity will change. It'll be a positive velocity dropping to 0 and then becoming a negative velocity. But the acceleration is always constant and always negative. So for a negative x squared graph, for throwing something up in the air, the second derivative is always negative. If it's going up more and more slowly, and if it's coming down more and more quickly. In both cases, the upwards velocity is always decreasing because gravity is pulling it downwards. In the case of this positive x squared graph, no matter where you are in the graph, the gradient is increasing. As you move along, if it's a steep negative, it's becoming a less steep negative. Gradient of -5 becomes a gradient of -3, and so on. And if it's a positive, it's becoming more positive. A gradient of 1 becomes a gradient of 2, becomes a gradient of 3, and so on. See if you can mark on this graph, your y equals e to the minus x squared graph, any of the regions where the curve is convex. Think about both of those examples. See if you can identify the regions where the gradient of the curve is increasing. And when you've done that, let's look at concave. We remember concave because a cave, the typical picture of a cave is concave, the way it curves. We're thinking about something that goes over. So the graph of ln x is a good example of this. If I've used e to the x, I might as well use ln x for the opposite version. ln x is concave everywhere. It is increasing. That's the interesting thing about this one. It's always increasing. So its first derivative is always positive, but its second derivative is always negative. So if you look at the gradient, it's always going down. It's very, very steep positive when you're close to 0, but it becomes less and less steep positive as x increases. And the other one is y equals minus x squared. We mentioned this for throwing something up in the air. Well, this graph is always concave. The gradient is always decreasing. The function itself is not always decreasing. It's increasing when x is negative, and it's decreasing when x is positive, and it's stationary when x is 0. But the second derivative is always negative. For y equals minus x squared, the first derivative is minus 2x, and the second derivative is minus 2. It's always a negative number. It's a fixed second derivative in this case, and it's always negative, which means no matter where you are, the gradient is getting lower. If it's a positive gradient, like it is when x equals minus 2 on the picture, then as you move to the right, the gradient becomes less positive. Steep gradient like 3 or 4 becomes 2 or 3, becomes 1, becomes 0, becomes -1, becomes -2, -3. So if it's positive, it's getting closer to 0, and if it's negative, it's getting even further down, so further from 0. It's always decreasing gradient. See if you can mark on our graph the points where the curve is concave. And if you've done both of those, then hopefully you have already identified that there are a couple of key points in between. There's a moment when the curve changes from convex to concave, and then another point where it changes from concave to convex. Those points are referred to as points of inflection. And anywhere on a graph where the gradient is neither increasing nor decreasing may be a point of inflection. I say maybe because there are situations where it isn't, but in this particular case, on the graph we're looking at here, there are places where the graph changes from being convex to concave or concave to convex, and those are known as points of inflection, where the concavity changes or when the sign of the second derivative changes. That's when we're dealing with a point of inflection. Classic examples would be y equals x cubed, where instead of the traditional up to a maximum, down to a minimum, and then carry on up sort of behavior that you might expect to see with a positive cubic, we get the maximum and the minimum condensed together into one single point of inflection right in the middle. So with a standard y equals x cubed, at the origin, 0, 0, we get a point of inflection. The graph itself is either increasing or stationary everywhere. The gradient of the graph is decreasing when x is negative, getting less and less steep, and then it's increasing when x is positive, and there's a change takes place. This particular one is a stationary point of inflection. It's a change that takes place at a stationary point, but it's a change which makes it a point of inflection. It changes from convex to concave, or from concave to convex. In the case of y equals x cubed, starts out concave, ends up convex. For tan x, this one's interesting because this one is not a stationary point of inflection. Tan x doesn't have any stationary points. Once you learn how to differentiate tan x, if you've seen that one already, tan can be differentiated to get sec squared x. And because sec squared x is never 0, in fact y equals sec x is never 0, so sec squared x can't be 0, that means that tan x has no stationary points. There are no maxima or minima for tan x, and there are no stationary points of inflection either. But it doesn't mean that it doesn't have any points of inflection. It has a non-stationary point of inflection every single time it crosses the x-axis as it happens. So at 0, 0, and at pi 0, and at minus pi 0, and 2 pi 0, and so on. Every time the curve changes from being concave to convex, or from convex to concave. For tan, much like with x cubed, it starts out concave, has a wiggle, and ends up being convex. See if you can identify the points of inflection on our graph here. Let's see if you've got them all. The point I was making about an inflection point here, if you have a change of sign for your second derivative, then you've got what we call a point of inflection. However, there are graphs that have a 0 derivative, and yet that doesn't necessarily correspond to a point of inflection. The classic example is y equals x to the 4, but you can try higher powers of x and you'll find some of them have points of inflection and some of them don't. You'll see some of those in a second. So it's worth bearing in mind it's not enough just to say that a 0 value for the second derivative definitely corresponds to a point of inflection. That's not necessarily true. What does work is a change of sign. Now let's see if you found all the convex, concave, and inflection points on our graph. This is what we should find. There are 2 points either side of the graph. It is symmetrical, looks like about 0.7 something and minus 0.7 something. In between, we have concavity, looks like a cave, and either side, it's the increasing gradient, either positive becoming more positive on the far left, or negative but becoming less negative on the far right. So the graph is initially convex, changes to concave at a point of inflection, and remains concave all the way through the maximum. You might remember the second derivative test tells you that if you're at a stationary point where the second derivative is negative, it means you're at a maximum. And that's what's happened here. The second derivative is negative throughout that region, and at a certain point in that region, the first derivative happens to be 0. And because the gradient's decreasing and 0 at the same time, it means that it must have been positive previously, and it will be negative subsequently. If it's decreasing and it's currently 0, it's because it was higher than 0 before and lower than 0 afterwards, the gradient itself. So we have a couple of different things to be aware of. Now we've got first and second derivatives to consider. The graph is both convex and increasing in this first section. We have our inflection point there, which changes. It doesn't change the fact that the curve is increasing, but it does change the fact that the curve is no longer convex. The curve's concavity changes, so we now have concave, but still increasing. We reach a stationary point on the very top, and then we have still concave, but now it's switched across to decreasing. So the first derivative changes sign at a stationary point, but If it's a stationary point like a maximum or a minimum, the first derivative changes sign. But the second derivative changes sign at a point of inflection, like this other one here. And we end up convex again on the right hand side, but this time decreasing. So it's perfectly possible to have positive or negative values for dy by dx and positive or negative values for d2y by dx squared, and or zeros for any of those. Any combination of those is possible, and the really tricky ones are what happens when the second derivative is zero, because you can't tell without further investigation whether you're looking at a point of inflection or not. So let's look now at how we can use calculus to identify the regions on this graph which are either convex or concave. And as we saw before when we were looking at the first derivative, the thing we really care about are those boundary points, the points in between the concave and convex sections. We can see that this graph is convex either side of the two inflection points and concave between the two inflection points. So what we want to worry about is where are those inflection points. We start by differentiating because we're going to need to find the second derivative. We care about when the sign of the second derivative changes. The first derivative we've already got from before, minus 2x e to the minus x squared. The second derivative we can construct using product rule. I've done that and simplified it. You might want to work through for yourself to make sure it works the way it should. But minus 2x can be written down and then multiplied by the derivative of e to the minus x squared, which is also minus 2x e to the minus x squared. So the minus 2x and the minus 2x from that term multiplied together to give 4x squared. And then the next term has e to the minus x squared written down unchanged, and then multiplied by the derivative of minus 2x. That's where the minus 2 comes from in that second term. Now we're interested in when y is convex, so when the second derivative is positive, and we're interested in when it's concave, when the second derivative is negative, and also when it's zero. If we start with this inequality, then this will give us an inequality region at the end. But to solve an inequality, we start by looking for critical values. This is the same as when you're dealing with a quadratic inequality. The critical values will be the inflection points. So we could just find the inflection points and use the graph, if we already know what the graph looks like, to identify whether we should be either side of them or in between. Or do this as if we didn't have the graph. We start by looking for critical values, solving the equals 0 case. And you should notice that although we've got two factors, e to the minus x squared and 4x squared minus 2, one of those factors can never be 0. E to the minus x squared is always positive, so the only way we can make that entire expression equal to 0 is by setting 4x squared minus 2 equal to 0. Now that we could factorize further, but it would be a little bit messy. Instead, we just solve directly. Rearrange it, and we get x equals plus or minus 1 over the square root of 2. Those are the 2 points we're interested in, which fits with our estimation of plus or minus 0.7-ish. Then, if you like, you can draw yourself a quick sketch here. This is essentially just a graph of 4x squared minus 2. We're looking at a quick sketch of the quadratic bit of that inequality because that's what will determine the sign of that expression. Is it positive? Is it negative? Where does that happen? And if we want to know when y is convex, we're looking for when our expression is positive. That happens either when x is above 1 over root 2 or when x is below minus 1 over root 2. And a nice way to represent this is in set notation. So you use the curly brackets to represent the set of all values of x that are less than minus 1 over root 2, and then the union symbol to represent a set which is composed of everything in the first category and also anything in the second category. Those two categories don't overlap. You can't have a value of x which is simultaneously below the lower inflection point and also above the upper inflection point, but you can describe the entire set of all possible x values using this sort of notation. So we have convex graph when the second derivative is positive because the gradient is increasing. We have a concave graph when the second derivative is negative because the gradient is decreasing. But as we've seen, if the second derivative is 0, we're a little cautious about saying point of inflection. We can't necessarily say that for sure. That's the next thing we need to look at in detail. This is the key idea. We've touched on this before. What it means to be a point of inflection is for the function to change from convex to concave or from concave to convex. If there is a change in concavity for the function, it's not enough for the second derivative to dip to zero if all it does is go from positive to zero and back to positive again. That would effectively mean the gradient is increasing and then stops increasing for a second and then continues to increase. That's the kind of thing you might get in the graph y equals x to the 4, where the gradient's increasing as we move towards the origin from the left, and then it's neither increasing nor decreasing at the origin, because the second derivative of y equals x to the 4 is still 0 at the origin. But then after the origin, when x becomes positive, it's increasing again. That wouldn't count as a point of inflection, and that's because it's a local minimum point, and in some cases it might be a local maximum point. So it's important to notice that the second derivative test that you've used before, it's a one-way test. If you get a positive second derivative, then it is true to say you're looking at a minimum. And equivalently, you could say if you get a negative second derivative, it is true to say you're looking at a maximum. But the converse is not necessarily true. We can't say for sure that if you have a minimum, then the second derivative is positive. That does not follow, because you can have a minimum without having a positive second derivative. The classic counterexample will be y equals x to the 4. So we can look at these graphs. You can see that for some polynomials we obviously get a minimum, but it's quite a flattened minimum. That's because if you raise a number between 0 and 1 to the power of something like 4 or 6 or 8, or even 7 or 5, you're going to get a much smaller size of number. The sign will change depending on whether you have an odd or an even power, and that's why some of these graphs have a point of inflection in the middle and some of them don't. Think about whether they're convex or concave. When we look at x to the power of 6, the graph is convex always. The same with x squared, and with x to the power of 4, the graph is always convex. But when you look at x cubed, or if you look at x to the power of 5, you see a graph which is concave on the left and convex on the right. Those are the ones that have a point of inflection. The other ones in this particular collection, they have a minimum point. And of course, stick a minus in front and you've got a 0 second derivative, but a maximum point. And a quick reminder, y equals x cubed has a stationary point of inflection, which means that the first derivative is 0 at the same time as the second derivative changing sign. But you can have non-stationary points of inflection as well. We've mentioned tan x already. Here's another one. Y equals x cubed, add x squared, add x, add 1. That's quite a nice one. And you can see that before the point of inflection, which occurs just slightly to the left of 0, before that point, the graph is concave. So the gradient's decreasing, negative second derivative. And after that point, the graph is convex. The gradient is increasing. We have a positive second derivative. And it's a similar sort of behavior with tan x, although for tan x, the point of inflection occurs at the origin and also at the point pi 0 and so on. Now let's work through a tricky example. This one has quite a bit of working out involved. It's a good one to practice so that you build confidence and fluency with the key skills involved in differentiation. But we're going to focus on looking for the point of inflection. The question asks us to show that it has a point of inflection, which means we need to prove that the point we find is a point of inflection, and we need to find its coordinates. Well, we're not going to get very far without differentiating. We're going to need to start by finding the first derivative so that we can then find the second derivative. And it already looks quite messy, but all that's happening here is quotient rule, because we've got a fraction, and chain rule when we have to deal with e to the power of 5 minus x. E to the anything differentiates to e to the same anything multiplied by the adjustment factor, the derivative of the anything. So if you want to differentiate e to the 5 minus x, you're going to get negative e to the 5 minus x. We're multiplying by minus 1 because 5 minus x differentiates to minus 1. The rest of this is just the standard quotient rule, bottom d top minus top d bottom over bottom squared, and you can look up the formula in the formula book. There's no requirement for you to memorize that. When we simplify it a little bit, you end up with 4e to the 5 minus x over 1 plus e to the 5 minus x squared. Takes a bit of messing around to get there, but once you've got it, you have the first derivative, and you're ready to do the second derivative. Looks even messier. That's because we've got more awkward things now. We've got something complicated on the top and the bottom of the fraction, but it's still doable. If you look carefully, you'll still see the telltale signs of quotient rule. The denominator has been squared. That's why we've got 1 plus e to the something all to the power 4 now instead of to the power 2. And the bottom multiplied by the derivative of the top minus the top multiplied by the derivative of the bottom still appears. The derivative of the bottom requires some additional chain rule. It's something squared, which means you need 2 lots of the something to the power of 1 multiplied by the derivative of the something. And in this case, the derivative of the something means the derivative of 1 plus e to the 5 minus x, which is just negative e to the 5 minus x. So there's quite a few steps in there, and if you need to work out the derivative of individual pieces separately and then bring them in, that's fine. I would do that on a separate side of the sheet, make sure it's visible and it's clear, but maybe rule off so that it's not confused with the working you're currently doing. This will also simplify a bit. I've managed to cancel a factor of 1 plus e to the 5 minus x from the top and the bottom and bring a few things together. We've also got a factor of minus 4e to the 5 minus x, which I can pull out of the top. The next thing to do is to recognize that if we're looking for a point of inflection, the second derivative will be 0. That's not sufficient to demonstrate that it's a point of inflection, but it's a good way to begin to find one. If we're at a point of inflection, then it's true to say the second derivative is 0, but just finding a point where the second derivative is 0 is not necessarily enough to show we have a point of inflection. Let's start by finding it, and then we'll prove that it is one. So we set the second derivative to 0, and you'll notice straight away I've ignored the denominator. That's because if you've got a fraction that's equal to 0, the only way that can happen is if the numerator of that fraction is equal to 0. Now, part of this is something which can't be 0 anyway. E to the power of something is always non-negative and non-zero. It's always a positive value. So that can't be 0. Minus 4 can't be 0. We're left with the bracket. 1 minus e to the something must be equal to 0. And that is perfectly possible. All we need is for e to the 5 minus x to be equal to 1. And if you think that e to the 0 equals 1, you could jump straight to that. If not, you can take logs of both sides. Ln of e to the 5 minus x, the ln and the e to the power of are inverse functions, so they cancel out, you get 5 minus x, and ln of 1 is 0. So 5 minus x is 0, which means x is 5. We've got a nice whole number for the x-coordinate of our point of inflection. If we hadn't got a nice whole number, we would leave it in log form or whatever form it came out in, because unless you were told to give approximate values, which you're unlikely to be in a pure maths question like this, you should always give the exact values, even if they look messy. Now, in order to prove this is the point of inflection rather than just a possible candidate for a point of inflection, we need a change of sign. So we're going to investigate either side. Now, the logic here you'll need to work through carefully. We start by noticing that e to the power of 5 minus x changes from being less than 1 to being more than 1 as x goes from around the value x equals 5. So we're looking for a change of sign between those points. As x changes from being less than 5 to more than 5, what happens to our second derivative? We know that e to the power of 5 minus x will be less than 1 when the power 5 minus x is less than 0. Think about the graph y equals e to the x. When x is negative on that graph, e to the x is smaller than 1, and when x is positive on that graph, e to the x is bigger than 1. We also have the fact that if we rearrange a little bit if we're taking away from 1 this value, which is either less than 1 or more than 1, we get a result which is either more than 0 or less than 0. We also know that minus 4e to the 5 minus x is less than 0 for all values of x, because e to the 5 minus x is positive for all values of x. And therefore, we can see we've got a change of sign at x equals 5. That proves we've got a point of inflection. And the final step is to take your value for x, which is 5, and substitute it back into the original function 4 over 1 plus e to the power of 5 minus 5. Luckily, this also cancels down nicely. 5 minus 5 is 0, e to the 0 is 1, 1 plus 1 is 2, 4 over 2 is 2. Finally, this is what the graph looks like. If you were to sketch this, it heads off forever to the left, getting closer and closer to 0, and forever to the right, getting closer and closer to a y value of 4. But this curve is known as the logistic function curve. You may have come across this if you're looking into some of the COVID-19 predictions. This is typically used to model the spread of an infectious disease, where the initial growth appears to be exponential, because the more people catch it, the more people catch it. But after a certain time, sufficient number of people have caught the disease that the disease can't spread so effectively. If 80% of the people around you have already had the disease or already have the disease, then only 20% of the people can catch the disease from anyone who's spreading it. And that's why what starts out as almost exponential growth ends up looking more like exponential decay towards the end. Of course, depending on what kind of measures are in place, the height of this curve will change, and you can affect that by messing with the value on the top of the fraction. And the rapidity with which the curve reaches it can change. That gets impacted by messing with what goes on in the power of e. And finally, now you can try exercise 9i in the book to test out everything that you now know about how to differentiate functions, e to the x, ln x, trig functions, along with the information we've now got about how the first and second derivatives can give you information about stationary points and points of inflection. I want to finish with a little bonus section. This is based on one of the challenge questions in the book, the hidden symmetry of the cubic graph. Like me, you probably thought when you first came across cubic graphs, these are not as nice as quadratics. They don't behave quite in the predictable manner that quadratics do. They certainly don't have the nice symmetry that a quadratic graph has. You may well have been caught out by assuming that the stationary points of a cubic lie exactly in between two of the roots of a cubic, but that turns out not to be true. In fact, a cubic might have one root, it might have two, it might have three. If it has two roots, maybe one of them's a repeated root. There doesn't seem to be any particular pattern behind the roots and behind the stationary points. Sometimes we've got one root and no stationary points. Sometimes we've got one root and two stationary points. We just can't tell. Maybe one root and no stationary points, like this one. But there always seems to be a point of inflection. A cubic graph will be like this one, concave followed by convex, or if it's a negative cubic graph, convex followed by concave. So there might be something in it. If we start differentiating, we might see something come out. Here's a general cubic graph. If you type this into GeoGebra, you'll get sliders for A, B, C, and D, and you'll be able to make them play and give you something like the animation we've got here. But if we differentiate, we can get a general expression for the first derivative for our general cubic graph. And if we differentiate one more time, we'll get the second derivative. And you can already possibly start to see where the symmetry is going to come in. It's more subtle than for a quadratic, but that's because we have to go to the first derivative before we find it. The symmetries that a quadratic has in terms of its roots and its stationary point are the same symmetries that a cubic has in relation to its stationary points and its point of inflection, because the first derivative of a cubic is a quadratic and the second derivative is the first derivative of that quadratic. So we'll see what happens when we find the point of inflection. We just need to set the second derivative equal to 0, and it's a nice straightforward linear equation. One of the upshots of this, of course, is that there is always a point of inflection for any cubic. As long as it's a cubic equation, we're not going to have a problem calculating negative b over 3a. If it doesn't have a value for a that is not 0, if the value of a is 0, we're not looking at a cubic equation in the first place. So provided a is non-zero, we've got a cubic, and provided we've got a cubic, we've got a point of inflection. And we can quickly and easily find it. It may be next to impossible to find the roots of a cubic, but we can find the coordinates at the point of inflection just like that. Now, let's look at the stationary points as well. Go back to the first derivative. It takes a bit longer because it's a quadratic. But remember, we've got the quadratic formula for this. Got to be a little bit careful because we have an a, b, and c in this equation, and the quadratic formula involves an a, b, and c. But in place of a, we've got 3a. In place of b, we've got 2b, and we have a c for c. So we've got to be a little bit careful. The formula turns into negative b, which in our case is 2b, plus or minus the square root of b squared, which is 2b squared, minus 4 times a times c, which in our case is 4 times 3a times c, all over 2a becomes 2 lots of 3a. With a bit of simplifying and rearranging, we can see that this is equivalent to negative b over 3a plus or minus some other stuff. The negative b over 3a is what I'm interested in here. It's exactly the same term that we got when we looked for points of inflection. And what this means is the stationary points will be point of inflection plus something or point of inflection minus something, where the something is the same something. It's just like what we see with quadratics. We might have roots of 3 plus or minus root 7, and the vertex, that happens when x is 3. So the roots will be equidistant from the vertex for a quadratic, and we find for a cubic that the stationary points are equidistant from the points of inflection. In fact, we can even go a bit further than that. We've got rotational symmetry around the point of inflection. The entire cubic graph can be rotated 180 degrees around its point of inflection, and you will end up with exactly the same graph. You can see that for y equals x cubed, the most fundamental one. You can kind of make sense of why that should work, but provided you rotate around the point of inflection, that same symmetry you appreciate with y equals x cubed is in every single cubic graph.